Okay guys, in this video we are going to be talking in more detail on the subject of reaction mechanisms. Most stoichiometric reactions have a complex mechanism that consists of a sequence of so-called elementary reaction steps. Okay? And these involve different intermediate species that are formed along the way between the reactants and the products. The difference between a stoichiometric reaction and an elementary reaction step is that the elementary reaction step represents a single chemical collision event that has no intermediates. So for example, you could write in this generic example that we have, you could write a stoichiometric equation that looks like this. However, you don't necessarily know if the reactants directly form the products or not, or whether or not, like we have here, whether or not different intermediates are formed along the way. And so the stoichiometric reaction really only tells you what do you have before the chemical transformation, and then what do you have after the chemical transformation has been completed. The mechanism, on the other hand, will show you all of the individual steps along the way. And each of these steps represents exactly what you see. It represents a collision between those reactants to form the products that are given at the end of that step. And that may be an intermediate, as we have here in these initial steps, and then the final step would give you the products. We've already learned, and I'm just repeating it here, that the rate law for a stoichiometric chemical equation cannot be determined from the stoichiometric coefficients. You have to do experiments in order to determine the rate law for a stoichiometric reaction. However, for an elementary step, because what you see is what you get in terms of a single collision event, the rate law for the elementary step can be deduced from its chemical equation, and this is related to the concept of molecularity, which applies to elementary chemical reaction steps. So the main point of this slide is to distinguish between an overall stoichiometric reaction, which may involve one or more intermediates through a complex mechanism, to distinguish that from an elementary reaction step, which is a fundamental chemical event where reactants come together to form the products with no intermediates in between. So when talking about the molecularity of an elementary step, it basically refers to the number of reactant molecules in that elementary step. And so for an elementary step where you have a single entity becoming a product, we call that unimolecular. And so that would have a first order type of kinetics. So the rate for this unimolecular elementary reaction step would be a rate constant times the concentration of that reactant. For a bimolecular reaction, there's two types. In type 1, the two reactants involved are of the same species. And so that is going to give you a second order reaction of a second order kinetics of this form, compared to type 2, where the two reactants are different species. Here, the reaction rate for this elementary step will be first order in species A and first order in species B, and it's overall second order. Okay, so both types of bimolecular reactions give you second order kinetics. It's just that the bimolecular type 2, it's first order in each of the different reactants. For a termolecular elementary step, there's three types. If all three species are the same, you get this rate law for the elementary step. You could have two of the reactants being the same and one of the species being different. That also gives you a third order rate law, but it's second order in species A and first order in species B. And if all three species happen to be different, this would be term molecular type 3, where the rate law is first order in each of those species, but still third order overall. To my knowledge, there has never been observed a tetramolecular elementary step or anything larger than that. So those events, if they occur, are so rare that they have yet to be observed to contribute in any meaningful way to a chemical reaction. The last point I wanted to emphasize is that the molecularity of an elementary step cannot be inferred from the observed reaction order. That is to say, even though you have the empirical rate law, you have the rate law that's derived from the experiments, you can't infer what the molecularity of the species are in the mechanism. Okay, so you can't go backwards. Now, if you know the mechanism, if you know the true mechanism for the stoichiometric reaction that you're talking about, you can derive the rate law from the elementary steps. However, you can't go the other way in general. So here we are, what we're supposed to do is to take these chemical reactions here and express the rate law for them. Now, I've pulled this problem from a different textbook, and in that textbook, the author uses a single arrow to denote a stoichiometric reaction and elected to use this sort of hollowed arrow to denote an elementary step. So that author actually distinguishes in the chemical equations themselves, which is a stoichiometric reaction and which is an elementary step. So the answer for part A is that you cannot deduce the rate law for a stoichiometric reaction. So you can't provide an answer for part A. However, because the author told us that parts B and C are elementary steps, we can write the rate law for those. So for part B, you would write the rate for that step would be whatever the rate constant is, let's call it Kr, is going to be the concentration of ozone, because ozone appears once as the reactants, times the concentration of chlorine. So it would be a bimolecular type 2 reaction. The same thing for part C. It's also a bimolecular type 2 reaction. So you would have NO2 times the concentration of fluorine. So those are straightforward. We're going to do some more examples of this, looking at elementary steps and writing out the rate laws for them in this lecture. Let's see here. So here we've got a bimolecular elementary reaction, and it says there is evidence that the mechanism for this reaction is a single elementary step. What would be the rate law? So the author is telling us this should be an elementary reaction step. What would be the rate law for it? So for this one, we would write the rate would be whatever the rate constant is for this particular step times the concentration of the methyl iodide times the concentration of the acetate ion. So again, bimolecular type 2. Here we're going to look at a specific mechanism. This is called a consecutive pair of elementary steps, and each of the steps is unimolecular. So we have our reactant A forms an intermediate I, and there's a rate constant for that step, and then the intermediate I forms the product, and there's a rate constant for that second step. We're going to suppose that initially there's no intermediate or product present, so at time t equals 0, the concentration of the intermediate and the product are 0, such that at any time later, the concentration of and this is also based on the stoichiometry, the concentration of A at some time plus the concentration of I at some time plus the concentration of P at some time all equal that initial concentration, always, for all time. And here's what we should expect. We should expect the concentration of A to decrease from its initial value. The concentration of I is going to go up, and then it's going to start coming down, and as it starts coming back down, the concentration of the product is going to start increasing. So that's generally how this type of mechanism works. Well, what we've done over here is I've written out the rate laws governing each of the different species' time dependence. And so what I wanted to review, while we've got the answer kind of sitting here in front of us, I wanted to show you what's going on. Essentially, you need to be able to write down these types of equations, these differential equations, by looking at the mechanism. And so I want to illustrate how I do that. So, for example, suppose the problem was express the time derivative for each species in this mechanism. Okay, that's essentially what we're doing. So you want to write out the expression for how does the concentration of A change with respect to time. And here's how I do that. I take a look at the mechanism and I find species A. Okay, and I see that in this first step, the concentration of A decreases. Okay, so this first step is going to give me a negative term for the change in A, right? The first step is going to cause A, the concentration of A, to decrease. So I put a minus sign. I see that the reaction is unimolecular in species A, so I can write it as the rate constant for that step times the concentration of A. A only appears once in this step, and so it's going to be first order in that term. And there's no other steps involving species A. Okay, so that's the whole equation we get for the time derivative of the reactant. Now the intermediate participates in two elementary reaction steps. It's the product in the first step, and so the first step increases the concentration of the intermediate. Here's the rate constant, and again, it's unimolecular in species A, so that's the term I get for the first step. Now the second step decreases the concentration of the intermediate, and so that's going to give me a minus sign because it's consuming the intermediate. The rate constant is Kb, and it's unimolecular in the intermediate concentration, like so. Finally, for the product only appears in one step. It only appears in the second step, and the second step increases its concentration. So it's going to be plus the rate constant times the intermediate. So that's the logic behind how these equations are generated. And like I said, we're going to practice this a few more times in this lecture, and this is something that I want you to practice in the homework as well. Now, what we have here, we have a set of coupled differential equations. That is, you can see that the differential equation for I involves not only the concentration of the intermediate, but it also involves the concentration of the reactant. Likewise, the change in the concentration of the product is tied to the concentration of the intermediate. So these differential equations are coupled together, and they need to be solved simultaneously. Now, this one can be done analytically, that is with pen and paper. But in general, for more complicated mechanisms, you often cannot solve them with pen and paper. Nevertheless, they can be solved with a computer, and you're not really responsible for being able to do the pen and paper solutions, nor the computer solutions, at least in this lecture. And so what I've just done is written on the right hand side. I've written the solutions to these coupled differential equations. And you see that while the equation for A is rather simple, it's just exponential decay, first order, as you might expect just by looking at the differential equation. You can see that the solutions for how I changes as a function of time and how the product concentration changes as a function of time are complicated. But like I said, they're more complicated, but they're not. In the end, they're not that complicated. Here's a graphic showing what they look like, and it reflects just what I said at the beginning of this part, is that your concentration of species A is going to decrease, right, exponentially, first order kinetics. You see that the intermediate concentration starts at 0, it goes up, and then it starts to come back down. While it's coming back down, you see the product concentration starts to increase. Okay, so A starts to react, you start to build up intermediate, then the intermediate starts to fall apart into the product. Okay, so that's the important thing that you need to understand about these types of consecutive elementary reactions. You don't have to have these equations memorized by any means, although it is useful to keep this type of diagram in your mind and being able to read the diagram. Let's see. So here we have an example problem. This is really more of just a calculus problem, so there's nothing too there's not a whole lot of information gained in it, although it does illustrate why you might want to master chemical kinetics, because this is sort of a practical problem. So suppose that you are, working in industry and you've got some sequential mechanism going on, and what you really want to sell is the intermediate, not the final product. The final product is worthless. And so the idea of this question is how do you generate the maximum concentration of intermediate? Okay. That is, you want to stop this reaction when the concentration of the intermediate is greatest, right? Because the product is worthless. So if you wait too long, all of your valuable intermediate is going to have reacted away, and you'll be stuck with this costly product that you need to remove. So the question is, at what time does the concentration of I reach its maximum? And that's a calculus problem. So what you want to do is to take the time-dependent function for the intermediate. You want to take its first derivative and set that equal to 0, and then solve for t. Okay, so that's the concept from calculus. The rest is really details. And so if you just take this time derivative, you get Ka over Kb minus Ka. The derivative of the exponents, you're going to get minus Ka e to the minus Kat. That's going to give you plus Kb e to the minus Kbt times A0. You're going to set that thing equal to 0. You can cancel out the constants. You're going to have then Ka e to the negative Kat equal to Kb e to the negative Kbt. You can rearrange, so we'll do we'll rearrange and then take the natural log of both sides. So we'll do natural log of Ka over Kb e to the minus Kt equals natural log of e to the minus Kbt. Break this up using logarithms. Okay, then you want to, combine the terms. So you'll make it, which way do we want to go? I guess we'll go this way. So we'll go Ka minus Kb times t equals the natural log of those, and then you just solve for the t. T will be natural log of Ka over Kb, and all that's divided by Ka minus Kb. I think I did the algebra correctly after that, but anyway, that would be the time at which the function peaks. And then the second part of the problem, which I won't do, involves taking the function for I and then plugging in that time, plugging in t equals natural log of Ka over Kb, Ka minus Kb. That is going to then be equal to your I max. And then so you'll get an expression for that in terms of Ka and Kb and the initial concentration. So really just substituting that in here. I won't do that. It's just extra algebra, and I don't think it gives you a particularly simple result. So we'll just leave it at that. Moving on to the next portion of this topic. The steady state approximation is a useful way of thinking about intermediates under certain conditions. It is an approximation strategy, and it allows, and like all good approximations, it allows you to simplify the equations you're dealing with. It's valid when the intermediate concentration is small and does not change very quickly. That is, when the intermediate concentration changes slowly. Under those conditions, you can approximate the time dependence of the intermediate's concentration. You can approximate it as being just 0. Okay? And that, as you can see down below, that simplifies the equations that you're dealing with. So it doesn't help you here in this differential equations for species A, but for the intermediate concentration, time dependence, we're basically setting it equal to 0, which allows us to then take this equation and solve for the intermediate concentration. And so this is the result that you get. Okay, so this is the steady state approximation for the intermediate concentration. And if you take the time dependence of species A, that gives you the time dependence of the intermediate. It also allows you to simplify the expression for the product. So it gives you this expression for the product concentration versus the derivative with respect to time, which you can then integrate to give you the time dependence of the product's concentration. And so if you compare these equations here to these equations, you can see that the steady state approximation indeed simplifies the equations. This figure here, so comparing this figure, where we get quite a large amount of intermediate forming, the steady state approximation is only valid when the intermediate concentration does not get very large and it's more or less steady with time. And the reason it's steady with time is because the reactant is constantly producing intermediate. As the reactant reacts, it produces the species I. It's just that species I reacts very quickly to form the products. And as a consequence of that, the intermediate concentration does not build up very quickly. Or it doesn't build up very large because it reacts immediately. Okay, so this is the mathematics of the steady state approximation, and this is the graphic that goes along with it. What this slide is doing is it's comparing for the case where, just going back to our mechanism, just to write that out explicitly. We've got a mechanism that looks like this, and there's two rate constants, Ka and Kb. And so what they're saying is that Kb, the rate constant for the second step, is very large compared to Ka. So as soon as the intermediate forms, it reacts rather quickly because this is going to have it has a large rate constant. And so as the reactant forms the intermediate reacts right away. And so what you're looking at here in the solid curves would be the actual, the exact solution for this problem. Okay, that is, they are these functions here for the case where Kb is 20 times Ka. Okay, and so the solid curves are exactly what you get. The dotted curves, however, those are the results for these steady state equations, these simplified equations. And you can see that while there is a difference between them, that qualitatively they're correct, they're not very good at small times. However, at longer and longer times, they're better and better. And with any approximation, you lose some accuracy somewhere. And so that's what this slide illustrates, is where you lose that accuracy. It's at the short time behavior. And if this statement is not true, then the steady state approximation will be horrible, right? So if the intermediate concentration does build up in your reaction mixture, you should not be using the steady state approximation. When can you get away with using the steady state approximation? You can use it when this second rate constant is large compared to that one. Okay, so if this second step is very fast compared to the first step, you're going to be able to get away with the steady state approximation. So here is a much more elaborate example involving the steady state approximation. What they would like us to do is to devise a rate law for a complex mechanism. So this isn't a sequential mechanism. It's more complicated than that. We've got a forward step, a backward step, and then these two steps as well. And then this is the overall stoichiometric reaction. Incidentally, I want to point out that if you have the correct mechanism for a reaction, you should be able to add all of these steps together. The intermediates will cancel out, and it's going to give you the stoichiometric reaction. I should point out that you may have a mechanism that is incorrect that could also add together to give you the overall stoichiometric reaction. So mechanisms are difficult things to establish. It's possible for many different types of stoichiometric reactions to come up with plausible mechanisms that appear to give you the correct stoichiometric reaction. Nevertheless, they are distinct mechanisms, and one of them is correct and the other one is not. So there's this many-to-one problem where you don't necessarily know whether or not you have the correct mechanism. I think I have some comments on that, perhaps in a different video for us. In any case, what are we being asked to do here? We're being asked to derive the rate law for this given mechanism down below. And so we're going to derive the rate of the reaction. We'll derive it in terms of the consumption of the reactant. So it should be minus 1/2 dN2O5 over dt. So what we're going to focus on is constructing this time derivative here. So what terms contribute to this time derivative? Well, we see that the dinitrogen pentoxide appears in the first step as a reactant. And so the first step is going to decrease its concentration. There's the rate constant, and it's going to be unimolecular. Now, the reverse step of that first chemical equation in the mechanism produces N2O5. So we need to take that into account. So that reverse step is going to increase the concentration, Ka prime, and then it's going to be bimolecular, type 2. We also find the N2O5 in the third chemical equation of the mechanism, where that step decreases its concentration. There's its rate constant, and then it's bimolecular type 2. There we go. Now, what I want to point out is that this rate law involves products, which is not necessarily incorrect, but it also involves intermediates. And while it's not incorrect, it's not very helpful to express the rate law in terms of intermediates, namely because intermediates are hard to pin down in a chemical reaction. It's hard to measure the concentration of an intermediate because they often react very quickly. And so what we'd like to do is to eliminate these intermediates. Now, we're going to use the steady state approximation and just hope that it's valid. But really, you would need to investigate whether or not you're allowed to use the steady state approximation. So I really just want to illustrate the mathematics here. We've already discussed how to know whether you can or cannot. In order to know whether you can or cannot, you need to do some experiments. Let's suppose that we can. And so what we want to do is establish expressions for NO3 and NO based upon the steady state approximation. So we'll start with our first intermediate here, the NO3, and we want to write out what would its time derivative be. Well, we see that the first reaction and its reverse reaction both produce and consume NO3. So we're going to have a plus Ka into O5, and then there's going to be a minus Ka prime NO2, NO3, and then we find that the NO3 is being consumed also in the second step, like so. Okay. And now the essence of the steady state approximation is to say that this time derivative is approximately 0, which will be true if the concentration of NO3 doesn't get very large and doesn't change very much with time. Now what we can do is solve for the NO3 concentration. Okay, so I'm going to do some algebra, most of it in my head here, to write out what would be the steady state approximation for the NO3 concentration. And I believe it's going to be Ka prime plus Kb times NO2. Okay, so this is the algebraic rearrangement of this equation. What we're going to ultimately do is to substitute this into that equation there. But we also need to do the same thing for nitrogen monoxide. So I'm going to get the steady state approximation for the nitrogen monoxide. So this time derivative, we see that the nitrogen monoxide, it's produced in the second step. So there's going to be a plus Kb, NO2, NO3. And it's consumed in the third step, so minus Kc, NO into O5. We're going to set that to be 0, and we'll solve for the nitrogen monoxide. I think that's correct. We can go further. Because this involves NO3, we can substitute that steady state approximation into this steady state approximation. And we see that the NO2s are going to cancel out and the N2O5s are going to cancel out. So this is going to end up being a constant. It's going to be Ka times Kb over Ka prime plus Kb times Kc, and the concentrations all cancel out. So the next step is to take these two concentrations and to substitute them back into this original expression. So I'll go back to that. So we'll have this minus Ka into O5 plus Ka prime, and then I'll go ahead and do it explicitly. We've got the NO2, now we're going to do the NO3. So that's going to give us Ka into O5 over this sum of rate constants times the NO2 concentration, and we see that that's going to cancel out. We've got one more term here. We're going to have minus. It's going to be Kc times that. We notice there's a Kc in the denominator here, so I'm just going to go ahead and cancel it out. So we'll have Ka Kb over Ka prime plus Kb, and then it'll be times the N2O5 concentration. Now what we can do is factor out the N2O5, and so we'll be left with minus Ka plus, this will be Ka minus Ka Kb over Ka prime plus Kb, all times the N2O5 concentration. And I believe this further simplifies. Unless I made a mistake somewhere. Let's go ahead and rearrange it. So we'll have minus Ka prime minus Kb, minus Ka Kb minus Ka minus Ka Kb, all of that over Ka prime plus Kb and so we see that, so I was expecting, this should be plus by the way, I was expecting these two terms to cancel, and I feel like I've made a mistake somewhere in doing so. Doesn't look like it. Here it is. Right there. That should be Ka prime. So it does cancel out. Ka prime, Ka. So those two terms cancel out. And then what we're left with is minus 2 Ka Kb over Ka prime plus Kb times the N2O5 concentration. And if we go back to the rate, which is minus 1/2 that time derivative, we get Ka Kb over Ka prime plus Kb, such that the overall rate is first order in the dinitrogen pentoxide, and then the effective rate constant, that is, the observed rate constant, is actually a combination of rate constants from the mechanism. So this is what you would observe experimentally, and then the observed rate constant is actually a collection of rate constants from the mechanism. So that illustrates one application of the steady state approximation. Here's another one. This one is a bit easier, hopefully. I wanted to go through at least two of them to to illustrate how to generate these differential equations. So we'll do another example, this one involving this ozone reaction. We have some of the steps in the mechanism, not all of them, but we have the important ones, let's put it that way. So what we want to do is express the rate of reaction will be minus 1/2 the rate of reaction of ozone, the rate of consumption of ozone. So this is what we want to get. We'll focus in on this time derivative, and we want to generate the equations governing how the concentration of ozone changes. So the first step in the mechanism decreases the concentration of ozone, so we're going to have a minus sign. It'll be Ka, and it's going to be a unimolecular step, right? So this is coming from this first forward direction. Now the reverse step, that produces ozone. So we have a plus sign, it'll be Ka prime, and then that's bimolecular type 2, like so. And then the last step in the mechanism also decreases the concentration, and that's again bimolecular type 2. Now we can do a little bit of simplification here. Let's see. Let's write minus KaO3 and I will pull out the intermediate concentration. So you see that the oxygen in this reaction is an intermediate. It doesn't appear in the overall reaction. Let's use the steady state approximation to evaluate the intermediate's concentration. So starting with the time derivative for the intermediate, we see that the first step produces the intermediate. The reverse step consumes it. And then the last step consumes it. Now, steady state approximation, set that equal to 0, and we'll solve for the oxygen concentration. I believe that's correct. So this guy now gets substituted in here. So we're going to put KaO3, and then I'm going to make this the denominator, Ka prime O2 plus KbO3. Wouldn't it be convenient if the signs were the same and you could just cancel that? They aren't, so we need to rearrange. And so we're going to be taking this expression, multiplying it by that one, and then dividing the whole thing by that denominator. So we're going to wind up with a minus Ka prime O2 O3 minus Ka Kb O3 squared, and then that's going to be, I'm going to be continuing that numerator, plus Ka prime Ka O2, and that'll be O3 minus Ka Kb O3 squared. So this is now the numerator, and all of that is divided by Ka prime O2 plus Kb O3. I didn't do this in the most elegant way, but you can still see the cancellation. This term cancels that one, and these two terms are the same. So it does simplify quite a bit. So we're going to have minus, looks like minus 2 minus 2 Ka Kb O3 squared, and then I'll never remember the denominator, Ka prime O2 plus Kb O3. And so that, and we recall that the rate was minus 1/2 that value. So we'll get rid of that minus 2 when we plug it in. And that's it. Okay, that's the rate law. You see that it's complicated. It doesn't simplify to a nice 0th order, 1st order, or 2nd order kinetics. And that's very often that's very often the case. If you have a complicated mechanism, you have a complicated rate law, and that's just all there is to it. So that's what we get here. We'll move on to the next concept here, the idea of a rate determining step. The notion here is if you have a number of elementary steps in your mechanism, it's the slowest step that determines the reaction, the overall reaction rate. So the chemical reaction can proceed no faster than the slowest step, and more technically, we should say the step with the smallest rate constant, at least usually. Let me give you just a graphical example. So suppose we're considering a sequential mechanism like this one, and the first step has a small rate constant, but the second step has a large rate constant. That means that, on its own, that second step is going to proceed quickly. It's the one with the small rate constant, the step with the small rate constant, that's going to slow down the overall chemical reaction rate. So all steps will have the same rate, but it's the slow step that determines what that rate is going to be. I should say it's the step with the smaller rate constant that determines what that chemical reaction rate will be. In panel B here, it's the reverse. The second step has the small rate constant, and the first step has the large rate constant. Even though this first step would proceed on its own with the high rate, it's the rate determining step, the slow step, that's going to make the overall process slow. So all steps will proceed with the rate of this slow step. It can get more complicated. Suppose we had a sequential, so we have a mechanism that can follow a sequential sequence, but suppose that there's also a pathway which takes you from the reactant straight to the product as well. In this case, where the direct reaction also has a large rate constant and would be therefore fast, it really doesn't matter that this one has a small rate constant, because the reaction can proceed with that rate. Okay, so you can't always say that the step with the smallest rate constant is going to determine the overall rate of the reaction, because there could be another pathway in that mechanism which bypasses that slow step. Usually, we would say that this step isn't important in the mechanism. Even though it could happen, we would say that it does not contribute very much to the overall rate. And often we'll neglect steps like that, pretty much like we did in this example. Notice how it says an incomplete mechanism. That means we left off some steps that aren't that important. And that would be an example. Okay. Here's another way of visualizing it, this time in terms of activation energies. So suppose that you have a sequential reaction like this, and this is the potential energy profile of the different intermediates. So we have our reactants, there's a transition state to the first intermediate, a transition state, then the second intermediate, then a transition state, and then the final products. The rate determining step, the one with the smallest rate constant, has the largest activation energy, and that's what slows everything down. So you have to overcome the largest barrier first, and the rate at which you can get over the large barrier is going to determine how quickly you get from reactants to products. Here we're being asked to essentially analyze a reaction mechanism. Up at the top we have our stoichiometric reaction, so this is the overall reaction. This is there's two chemical equations, but 3 steps, because the first equation has both a forward step and a backward step. We are told that this is what the rate law is, and they want us to analyze the rate law for the case where the oxygen concentration is very large. And so what I'm going to do is I'm going to make the mathematical argument that since the concentration of oxygen is very large, that when we compare this rate constant to this quantity here, that because the oxygen concentration is very large, we can probably neglect Ka prime. So what I'm saying is that Ka prime, for the conditions with which they're asking us to examine this rate law, Ka prime is much, much less than Kb times oxygen. What that means is that you can neglect this term relative to that one. We're saying that this number is insignificant compared to that number. And so we can rewrite the rate as 2Ka Kb NO squared O2 over Kb O2, and we'll get a cancellation, and so we wind up with 2Ka NO squared. And so effectively, for large oxygen concentrations, the rate of this stoichiometric reaction will be second order in nitrogen monoxide. The rate limiting step, as indicated here, would be this first step, where the nitrogen monoxide are combining to form the intermediate. Okay, so this is the slow step. And then once that intermediate forms, it basically reacts right away. So this would be a fast step compared to the formation step. Let's look at another motif in chemical mechanisms, a so-called pre-equilibrium mechanism. So here we've got a bimolecular reaction step that forms an intermediate, but then that intermediate can also reform the reactants. Or the intermediate can then go on to form the products. And what we mean by a pre-equilibrium, it pretty much means that the backward step is going to be a lot faster than the step that takes you to the products. So what happens is you very quickly establish an equilibrium between the reactants in this intermediate. So an equilibrium is established there, and then every once in a while, a product is going to form. So this is the slow step. In this case, since there's an equilibrium between the reactants and the intermediate, what you can do is set the forward rate equal to the reverse rate, and then solve for the intermediate concentration. Okay, so this would, in this case, it would give you I equals Ka AB over Ka prime. And then for this rate of formation of the product, you can substitute in this expression for the intermediate, and then you wind up with this second order kinetics expression. Right? It's first order in species A, first order in species B, but the observed rate constant is really a combination of rate constants from the mechanism. So the final step, as it says at the bottom, the final step controls the rate, but the pre-equilibrium controls the formation of the intermediate through this relationship here. So here they're asking us to, I don't know what they're asking us to do. Are they just asking us to do this? Okay. What they're asking us to do is to take a look at this same mechanism, but come at it from a different point of view. come at it from the point of view of the steady state approximation. And so here we'll focus in on the product. We'll calculate that time derivative, and we'll compare it to this result here. So in that case, we've got Kb times I, and from the steady state perspective, we would look at di dt, and we see that the first step produces the intermediate, so it's plus Ka bimolecular type 2 reaction mechanism. The reverse step consumes it, and that's unimolecular. And then the final step also consumes the intermediate. Okay, so in the steady state approximation, we just say that that's 0. Rearranging, solving for the intermediate concentration, give us an expression like this, and then we substitute that into our equation for the product time derivative. We get Ka Kb, that'll be over Ka prime plus Kb. We see that our effective rate constant here is Ka Kb over Ka prime plus Kb, which if we compare to what we had before, it's not quite the same. Not quite the same. However, if we let Kb to be much, much smaller than Ka prime, that is, if this second step is slow compared to this reverse step, then indeed that means we can neglect Kb relative to Ka prime, and we'll wind up with the same thing that we had from our pre-equilibrium assumption. Okay, so both approaches give you the same result if you make the same assumptions. Here's just another example of pre-equilibrium. And so they want us to show that this particular mechanism gives us a third order rate law. So let's start with the product. It's going to be Kb I times B from the second step of the mechanism. And we want to use a pre-equilibrium approximation here. And so we'll say that, going back to that first step, we'll say that the forward rate, Ka A squared, is equal to the backward rate, Ka prime I. And then we can use this to find the concentration of the intermediate once the pre-equilibrium is established. And then that gets substituted back into here. And we wind up with A squared B, which is indeed a third order overall rate law. And this is the effective rate constant, Kr. Here, our last little topic is discussing the difference between kinetic control of reactions and so-called thermodynamic control of reactions. So here, let's suppose that we've got two competing reactions. We've got reactants A and B. A and B can form one product, or they can form a different product. So this would be common in, organic chemistry. There's all sorts of byproducts and primary products. So you're interested in one particular product, but there may be byproducts. Each of these reactions is going to have their own, and we're assuming that these are elementary steps. Each of these is going to have their own rate, okay, and their own rate constant. Okay. The idea of kinetic control is that prior to chemical equilibrium being established, the distribution of products in the reaction mixture is going to be controlled by the relative rates. So whichever whichever rate is faster is going to be the one that dominates the products. So the relative amount of products is going to be determined by the two rate constants. However, at long times, after equilibrium is reached, thermodynamic takes over at a certain point, and the equilibrium distribution is determined by the relative Gibbs energies and the equilibrium constants for these two reactions. Okay, and that's given in terms of the delta G's. Okay, so this would be short time control is governed by kinetics, long time control at equilibrium is governed by thermodynamics and the Gibbs energies for the two reactions. Well, I think that's the last thing I had for you, and so I'm going to go ahead and stop this video here, and next time we'll look at some specific examples of reaction mechanisms.